For any DO-178C certification, you're going to have to provide evidence of analysis for timing and structure of your system software and design. If you've done safety critical before, you've done these analyses and provided the appropriate artifacts. Today, we want to discuss the analysis of worst case execution time in the multi-core environment, identifying and mitigating interference patterns that affect the to have disastrous results. For business reasons, minimizing the worst case execution time allows for more functionality. Well, in our avionics market, the FAA has formalized the position on these analysis, especially with regards to interference patterns, which affect your worst case execution time in a document called CAS 32A. The document provides guidance, generally taking the form of, did you consider this in your multi-core environment while you're addressing the DO-178C objectives? Stating that more precisely, auditors are going to ask, how are you going to manage your interference patterns and your resource contention while you're using multi-core? Highly recommended to get this document as soon as possible and evaluate for all your projects. And remember also, these certification efforts are a cooperative effort. You're going to have to address these concerns and your objectives with your COTS vendors, with your tool suppliers, and with the certification authorities. So the sooner you start coordinating, the better. Discussion today will be on the features that support meeting the objectives of the interface channels and resource usage, error detection and handling, and the safety nets. Additionally, for software verification, you're going to have to provide these analyses, so you're going to need tools to measure the effects of the features that you implement. Okay, to set the stage for the descriptions about the features and the tools available, let's take a look at the high-level Deos architecture. Deos is a fully modular microkernel architecture. The Deos kernel, depicted in purple here, is a module that is dynamically linked at runtime with all your other components, all your other software, to provide the functionality of the system to meet your system requirements. The binary Deos registry, depicted in orange, is the set of rules for space and time partitioning established by your integrators. Items like how much memory a partition is allocated and how much time an execution unit gets to run are represented in this binary. Using this registry, the Deos kernel enforces the rules. The partitions in dark blue represent a single address space for space partitioning enforcement, and then integration of the execution units within a partition, whether they're Deos threads or 653 partitions or POSIX P threads, support the time partitioning enforcement. RTOSs have to provide the ability for multi-core developers to eliminate and bound the resource contention, especially in those high impact areas like cache, memory access, device buses, for example, a PCI bus. RTOSs must also provide these features in such a way that the current execution is a performance advantage. Simply eliminating or bounding an interference, it's definitely not sufficient. The result has to perform at least as well as a single core solution. And ideally, if you're using multi-core, it's got to perform better than a single core solution. A combination of space and time partitioning mechanisms will be needed to address the various interference and performance issues. And safety nets as a last resort will be needed as well. Let's briefly talk about the RTOS features first, then we'll proceed to the main webinar topic of identifying and measuring the effect of the interference mitigation strategies in the Deos environment using the Rapita toolset. Here are the set of features that address CAS 32A concerns related to interference patterns and shared resources in the Deos environment. First, we have our safe scheduling. This is a bounded multiprocessing feature that allows the integrators to align the execution units, the threads, the 653 partitions or POSIX partitions, to minimize shared resource contention. Then we have memory pooling and cache partitioning. Cache and memory contention are the biggest hitters in the multi-core environment for performance, and thus a major concern. The integration strategy here is to minimize the cache misses. Also, if you're minimizing those cache misses, you're mitigating some of the memory bus contention concerns as well. These first two items are proactive integration solutions. CAS32 indicates you must detect and control poorly behaved applications, while safety nets are a reactive, on-target, platform-dependent software strategy to meet that goal. These are based on hardware-software interfaces available for monitors in the system. Additionally, you're going to have to defend all of your mitigation strategies. Keep in mind, again, this is a collaborative effort. We will defend our products and our strategies in any audits that you encounter. Okay, so let's start out with Deos safe scheduling. Timeline is broken up into windows. The number of windows, the length of windows are configured by your integrator to meet your system requirements. The window boundaries are identical on each core. We're showing 2 cores here, but the windows and the multiple schedulers that you see are applicable to a single core. By spanning the cores and the window boundaries, you get to define what schedulers can operate concurrently. And of course, you define what is actually executing in the context of each one of those schedulers. So let's think about that with regards to resource contention. By placing the use of a resource in different windows, you're controlling the use and contention. A simple example, you have a serial device output that you execute in core 0 on window 1, and then you execute that output again in core 1, window 2. You've separated them in time, you've separated them by cores, you are controlling the resource contention and use. Think about this as well with regards to previously developed binaries, software that you've set up for other programs. You're reintegrating to get multi-core efficiencies. You're not doing a full redevelopment. You know your applications. You can decide what can run concurrently. Example, you have a memory-intensive application versus a compute-intensive application. You could possibly run those in the same window on different cores to get some of the multi-core efficiencies. Note also here that we have multiple schedulers, the RMA, rate monotonic analysis, which is the Deos default, ARINC 653, and POSIX. The integration of these across the timeline is totally possible. This setup with the timeline also allows for mixed criticality application integration as well. So it comes down to your system design and integration to take advantage of these features to address the CAS32A concerns regarding shared resource contention. One other important feature that the kernel has, it imposes no cross-core locking. There are no core locks, no scheduling locks, no object locks. However, the idea of blocking can be interference or coordination. Application-induced blocking may be desired and useful behavior to support your requirements or design. If this coordination is implemented and you would like to use it, you'll need to describe it as such with regards to the CAS32A guidelines. The scheduling flexibility through our safe scheduling feature allows you to minimize interference and maximize the coordination to address the CAS32 shared resource contention concerns. So even with all of that, and you set up an effective scheduling implementation, the underlying hardware induces interference as well. It's pretty easy to visualize managing interference and coordination for peripherals that you add to the system. For example, say a PCI device. Most of your developers will understand that and how to coordinate the access to that. But the platform you choose has some interference natively, especially with regards to cache and memory bus arbitration. Shared cache contention is the greatest performance factor for today's processors. So, setting up a relationship to achieve the cache partitioning addresses the CAS32A concerns regarding the cache and memory interference patterns. The integration feature minimizes the cache and memory bus controller interference, and the defining factors are going to be the size of your memory and the size of your cache and the availability of cache on the hardware. Basic idea. Based on cache memory designs of modern processors, regions of memory pools, are associated with particular cache lines. The integration then allows you to assign those memory pools, which are associated with particular cache lines, to specific application partitions. Other key points here, this feature is patented. This does provide the best performance because the worst case execution jitter is reduced by minimizing or eliminating the cache thrashing between applications. Essentially, more cache hits, less cache misses. Because this integration activity to assign the memory pools takes advantage of the general cache operation, no application software integration or interaction is needed to manage the cache. For example, there are no hardware cache locking instructions used. In fact, many of the ARM processors, current ARM core processors, don't support cache locking. Since the cache partitioning setup is integration-based, this also helps you in certification efforts from platform to platform. It becomes much more simple to perform. The feature also can be used in single or multi-core environments. So let's talk about this a little bit. In the picture here, each of the applications 0 through 4 is allocated memory for use associated with particular areas in cache. App 1 or App 0, pardon me, uses pool 0, which uses cache lines associated with pool 0. Well, what does that mean? It means that cache used by the execution units, again, your threads, your 653 processes, your POSIX P threads, in App 1 are not affected by the cache usage in the execution units of the other apps. In other words, when the execution units in App 0 are not executing, their state is not changed. When they execute again, the cache state is the same as when they left. This maximizes the hits and minimizes the contention. In fact, with this depicted integration, the contention is isolated to the execution units in each application themselves, since each one is dedicated to a specific pool. Since you know your applications, this can be a significantly simpler analysis than if multiple applications were integrated and allowed to use memory that hit the same cache lines. So let's extend that a little bit. App 3 and App 6 represent the interesting cases here. App 3 uses memory from pool B, represented with the cache lines in the brown box in the shared cache. And you can note that App 4 and App 5 use memory from pool B as well. Well, space partitioning features of Deos prevent using the same memory within pool B, but the memory may share the same cache lines. And notice as well, these are across cores. So the execution units in App 3, 4, and 5 will affect the cache lines represented by the brown box. This is a totally possible integration. Your operational requirements and your design dictate if this cache usage relationship is acceptable. Now take a look at App 6, which gets to be the loner. In general, this would be a highly critical application where you really want to bound that worst case execution time effective cache thrashing. Notice the only application using memory pool C, which is represented by the purple cache partition block in the shared cache. So setting up these relationships through configurable integration parameters to achieve this cache partitioning addresses the CAS32A concerns regarding cache and memory interference patterns. Finally, let's talk about the safety nets. As developers, you've been designing all along to detect and respond to poorly behaved applications. Multicore just adds another dimension, since you're truly getting concurrent execution. Safety net allows you to monitor and react per your requirements to bad actors. Many of the new processors have performance monitor capabilities. Software designs can take advantage of these monitors and respond to performance threshold exceedance to deal with poor behavior. Resulting actions for the threshold exceedance is user defined. You can define whatever is most appropriate for your system requirements. So, supporting this worst case execution minimization theme, here are the features in the Deos environment. The proactive integration time capabilities of safe scheduling and cache partitioning give the system developers and integrators control over the timeline and the cache and memory to address the interference and resource contention concerns in CAS32A. And finally, there are the safety nets. Software can use the platform-specific features to detect and respond to bad system behavior. These all support the CAS32A interference concerns. All right, so you've done all your work. You have your ultimate design and your implementation to incorporate all of these features to address the CAS32A concerns. How do you measure and perform the analysis? Well, DDC-I and Rapita has coordinated to provide tools to analyze your multi-core environment. The DDC-I Open Arbor environment is configured to generate a project suitable for the Rapita RVS analysis tool. In the demonstration you're going to see, we're using a ZCU 102 platform. This is a Xilinx UltraScale Plus running 4 ARM A53 cores. Here's how we get it started. So I brought up a DDC-I Open Arbor environment with a workspace that contains multiple user projects, user application projects, and one platform project. For any reference platform or certified BSP that we supply, there will be a platform project in your distribution that you can instantiate in the Open Arbor environment here and then be able to use for your development. So to begin to use the Rapita tools and get set up for that, if you right click on the platform project, select Deos and configure Rapita, you will see in the console at the bottom a Python script gets run and multiple environment variables get set to be able to integrate and use the Rapita tools for your project. Additionally, you'll note that a Rapita folder has been populated now under the output directory here. The item of interest is this RVS project file. If we double click on that, that'll start the Rapita tool. So once this project is started in the Rapita tool, you now can begin the steps to integrate, instrument, and analyze the data of the code running in the Deos environment. With that, I'd like to turn it over to Dr. Sam Thompson from Rapita to discuss their data capture and analysis tools. Thank you.
Here we are, where Mike left off. Actually, there are 2 integrations in this project, so I'll go into the Rapitask only one for this part of the demonstration. In this workflow, there is only one option. It's a very simple workflow. I need to click on the Collect Trace button, and because of everything that Mike has configured through Open Arbor, all automatic configuration, RVS already knows exactly how to talk to the Deos target. So it is able to download the trace straight from the Deos target. You note that here there is a Rapitask only RVD, that's a RVS report file. It's got the red exclamation mark because the file does not exist yet, the report hasn't been created. The report will be generated once the trace has been downloaded from the target. There is absolutely no configuration necessary for this, other than what is carried out from within Open Arbor. It is a completely out-the-box solution. And as I said, there is no instrumentation involved either. It is zero additional overhead capability. This takes a couple of minutes, so I have jumped ahead. The guys at DDC-I are working with us as we speak to work on a faster mechanism for downloading the time map, for downloading the trace data. It's not horrendously slow. It took a couple of minutes, but we believe we can make this a bit faster. So you see our report file no longer has the exclamation mark. It now exists. It's been generated. Now there is relatively little in this report file because usually it would contain by default some analysis of the source code, but we can click the Rapitask button, which will load up the Rapitask trace that we have just generated. It looks something like this. And here we have a set of swim lanes for core 0, a set of swim lanes for core 1, for core 2, and if we scroll down a bit further we see we get some swim lanes for core 3 as well, showing all 4 cores. Now if we zoom out a little bit, start to see a lot more information on Deos. A lot of the system things execute on core 0, so we can see when tasks are being suspended, when they're starting, when they're completing. The same goes for all of the other cores. If we zoom in a little bit, we can see that not only are we getting the schedule information, but we get further information about what's going on Deos in the system. So we can see when windows are starting, we can see system ticks for each core. We get to see when tasks have completed, we get to see when exceptions are being raised. And if we scroll along a little bit further, we can find some other examples of events we can see. So Mike has already mentioned that slack time is a feature of the Deos kernel. So here we can see that this thread here has been granted some slack time by the Deos kernel. I can also, any task that you click on, if it has any events associated with that thread, then we see those highlighted at any zoom level. Now we can do some other cool things. One example, we can add additional metric fields. So I'm going to add a context switch intensity graph to my view. So now I can see the context switch intensity throughout the duration of my thread plotted as an additional set of swim lanes, if you like. So we could use this, for example, as a diagnostic tool to be able to see, oh, there's quite a few context switches happening here that we don't expect. What's going on? And we can then zoom in and inspect it further. Another thing we can do is we can look at the CPU utilization. So we can switch different cores on and off using these little buttons at the top. So here we see our CPU 0 is pegged at about 100% utilization virtually all of the time. In fact, this is expected. We were running one of our RapiDaemons, which we'll introduce in a second, on core 0. On core 1, however, we have an application running, so we can see there are some spikes in the CPU utilization, but we're generally hanging around 40 or 50%. Likewise in core 3, we are running another RapiDaemon, which is pegging it at 100%, and the same with our core CPU 3. There are many other cool features of Rapitask. If you're interested in these, please do get in contact. And that is all we have time for now. Right, and just one last thing to add. It was a fairly simple system which I demonstrated, but here is a screenshot showing 1.5 of 8 cores of a real customer system. So as you can see, Rapitask also scales very well to much larger and more complex systems. So after that quick introduction to what we can very easily achieve using Rapitask, I'll move on to introduce RapiTime. So RapiTime allows far more granular instrumentation and observation of time behavior. All the instrumentation is automated. We have a fully qualified instrumenter, so there is no manual review required for the source code once it's been instrumented. All of the results are from on-target measurement. There is no estimation. There is no interpolation or simulation involved. It is all what is really happening on the target. And because we can drill down really quite deeply into the time behavior of some software, then we can use it to also guide optimization efforts to work out exactly where we are spending most of our execution time, for example. So now we're going to cut to a demonstration. So we're back again where Mike left us. This time we're going to use the Deos target time map trace. And the first step, you're going to click the deploy button. Now the deploy button effectively runs some internal scripts inside RVS, which will finalize the configuration that Mike did through OpenArba. So I'm just going to go ahead and click OK. There are no further options I need to choose. This only takes a couple of seconds. It just deploys the rest of the integration library that we need. The next stage is the prepare stage. This is where we perform a static analysis of the source code. How this works is, again, the configuration that Mike exported through OpenArba tells RVS exactly where and how to run the whole DDC-I build system. So what we do is we build the entire project using the DDC-I build system through RVS, and we're able to use RVS to observe exactly what the compiler is doing. So we see all of the pre-processed source code as it is running through the compiler. For example, this means that we don't get confused when there is more than one main function, because every Deos partition has a main function in it. We don't need to second guess which functions are called from where and what's linked to what. We can observe all of this by looking at the compiler itself. And this takes as long as it takes to build your entire workspace. It could be a couple of minutes, it could be a bit longer. So I'm going to jump ahead right now. Cool. So we're now nearly finished the prepare stage. So after running the build system, our instrumenter is then called. Notice that we are using both our C instrumenter and our C++ instrumenter. There is both C and C++ in this project. We fully support mixed language projects, including any combination of C, C++, and Ada code. So I should note that there are no changes made to the original source code. That is left completely untouched. The instrumented copy of the code is a copy of the code, and it gets stored in the RVS database. We should also note that our instrumenters are fully qualified for DO178 processors, so there is no need to manually review the code once it's been instrumented. So once we've completed our static analysis, we can then go to the Analysis tab of our Project Manager, and we can see the structure of our source code laid out for us. So for this demonstration, I'm interested in a particular matrix multiplication, which exists in the periodic process 2, and so we can investigate the call tree. It's got a few functions inside it. So I'm going to right click on it and select this as a call tree root. This tells RVS that this is a call tree that we are interested in analysing. You note that some of the functions underneath our call tree, and there's a little red bar across them. That's because the implementation of this function isn't available. It might be because it's a library function, it might be because it's some inline assembly, could be some object codes that are being linked in, so we cannot instrument those functions directly. However, if we right click on them, we can select to add it as a black box function if we're interested in it. This tells our instrumenter that it wants to instrument each side of that function call, but we are not interested in that for the purpose of this demonstration, so I'll remove that setting. There are quite a lot of code in this workspace, and we can investigate quite deep down into some of the call trees. So for example, in this half algorithm, we can dig really deeply into call trees which we have the full implementation of. So it can be quite a powerful means of exploring the structure of some code as well. You can see lots of structural aspects which are not necessarily obvious from the code itself. So I'm going to now go ahead and click build. Definitely want to include our instrumentation in our build, and so what this does is it invokes the DDC-I build system over again, only this time at the point of compiling it. Rather than compiling the original uninstrumented source code, we inject the instrumented files into the build system, and so we build ourselves an instrumented executable. So now the build is completed, I'm going to go ahead and click run. So we want to run the report stage and open the results at the end of the run. So this basically analyzes the trace that we download from the target and combines it with the static analysis data which we gathered in the prepare stage. Now, because of the tight integration with Deos, RVS knows exactly how to communicate to the Deos target. This includes how to load binaries onto the target, how to reboot it, and indeed how to extract the trace from it, so there is no configuration necessary there. Currently the tracing, we just have a wait for about 10 seconds before downloading the trace for this example, but more configuration to, for example, download a trace on hitting a breakpoint through GTB is very possible. And currently it takes a while to download the trace data from the target, so I'll just jump ahead now to the end of it. So we have nearly finished downloading the trace data from the target. We then pass it to RapiDaemons to parse the trace, and RapiDaemons will then output a RapiDaemons report file, which should open automatically. So here we have our RapiDaemons report. You see that we have each of the functions in the call tree that we instrumented. We have execution time profiles showing the minimum, average, high watermark, and maximum execution time. I can plot things like the execution time profile. This cumulative execution time profile effectively showing us the number of executions that we saw that completed in less than a given execution time. Very useful for looking at the distribution of execution times that we have seen. We also get the same graphs for all of the subprograms that we saw and that we instrumented. Here in the invocations tab, you can see we saw 20 invocations of our instrumented root function. We can dig into that deeper if we want. We have contribution time. So the idea of contribution time is that something which executes a large number of times inside a root will make a larger contribution to the overall execution time, so we can use that for optimization. We can also dig deeper into some of our subprograms. So if I double click on any subprogram in my subprograms table, I then get a RapiDaemons report just for that subprogram, and we can even look at the individual instrumentation points that we placed inside that subprogram. And indeed we can dig down into some of the other features. So we can see here we had 3 nested loops which were looping over these matrices inside this multiply function. For this subprogram we have our invocations timeline, and we can even jump into our source code. So you can see everything that's highlighted in green was source code that we instrumented and that we also saw that we got execution time data for. So we get some very basic coverage data from our timing analysis. I should note that RapiCover has far more comprehensive and advanced coverage features than RapiDaemons does. Cool. So that should give a brief overview of the capability that we have natively with Deos in terms of RapiDaemons and RapiTask measurements. So now I will take you over some of the processes that we have in place to help you gain CAS32A compliance. So on this slide we have an image of our V model. So I'll quickly talk you through it. So in the top left we start out with our requirement specification. Quite often we'll start out with the requirements which are part of our DO178 requirements, for example, worst case execution time requirements. Once we've established the scope of our investigation, we then move down to the understand stage, which is where we want to start trying to understand the hardware platform that we are using, understand the software that we are running on it, understand the RTOS, and use this understanding to help us define our test methodology. Once we have an understanding of our test methodology, we could then move on to start designing our tests. It's at this point that I should probably break and introduce the concept of a RapiDaemon. In a multi-core scenario, it's often quite difficult to find out the maximum possible increase in execution time as a result of interference. In the top box here, we have a task running alone, a single swim lane, and we know that it is using a particular resource, at some point during its execution. Now, if we go to the second box down, we have 2 tasks running simultaneously on different cores. We know that both of these tasks may be accessing the same resource, but potentially at different times. So the worst case scenario in this case, which is explicitly required by CAS32A, is the worst case scenario, would be when these areas of resource usage align. Now, it is really quite difficult in the general case to ensure that particular parts of particular tasks will align perfectly on different cores. And particularly when we want to do this for many different resources and many different tasks. For this reason, we use RapiDaemons instead. So again, in a real situation, we might not even know exactly where in our tasks we are getting our resource usage. So to completely get rid of this problem, we use what we call RapiDaemons. They are very, very carefully designed pieces of code which will generate very, very intensive accesses to a particular resource. And they will do this all the time. So in this case, we don't need to worry about alignment if we are running a RapiDaemon on one core and the tasks that we are currently investigating on the other core, because we're using the resource all the time. We are always going to be triggering the worst case scenario for that particular resource. So with that context, it should hopefully be possible to see how we can use these RapiDaemons in our test designs to be able to explore some of the worst case scenarios that we might see in our system. Once we have designed the test or the tests, then we will implement these tests. We don't have time today to cover how we might use our RapiTest tool to do this. But we implement our tests for our platform and integrate our RapiDaemons. The next stage is the evidence gathering. So this is when we are executing our tests on our target and we're gathering the data and extracting them from the target. Then we move on to the assessment of these results, which is where we would analyze them in rapid time, where we would draw conclusions, decide whether or not we are meeting our requirements. And finally, we would generate some certification results. So this is what we might be putting in our SAS at the end of our certification process. I note here that we also have some feedback arrows going from right to left. So with complex multi-core platforms, it is not uncommon to find that some of our results don't match up with remotely what we expected. It could challenge some of the underlying assumptions we've made about our platform. So this may require us to go back and make some tweaks to our tests and some tweaks to our assumptions. So this gives us, roughly speaking, a 4-step process when we use it in reality. First of all, we would run our RapiDaemon in isolation on one core. And this will enable us to verify the actual behavior of our processor on a very well-known and well-defined piece of code. And then we would run the same RapiDaemon, again, instrumented with RapiTime for timing, but run other RapiDaemons on the other cores. So because a RapiDaemon will use resource really intensively, they're also sensitive to interference. So this is an experimental step which provides evidence, particularly towards Cascade to Objective Resource Usage 3, where we're characterizing the interference channels present on the hardware. Then we can move on to doing a similar process with our real software. So we start by fingerprinting our application. Something which we haven't covered today is that RapiTime, as well as reading timing information, it can also read performance monitoring counters on a target. So we can characterize the resource usage profile of an application. And then we can run our application against targeted RapiDaemons, which are targeting the resources which we've determined our application is using, and get some worst case behavior for our application under a range of different contention conditions. So again, particular link back to CAS32A. This will provide evidence for MCP software 1 objective. So this approach provides evidence of the actual behavior of the system, provides on-target measurement of interference